Tags are a text-based name for an area in the controller's memory. It can actually be alphanumeric, but it must, all tag names must start with an alpha character. They are just a mechanism for allocating memory, referencing data, blah, 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 blah. Minimum memory allocation is 4 bytes. So, anybody remember how big a byte is? How many bits? 8. 8. Says the programmer. Okay, so try to combine my E and my S there in a single character. A minimum of 4 bytes, and each byte is 8 bits. What is the minimum memory allocation for a tag? How many bits? 32. 4 times 8, 32. At least it was where I went to school. Okay. Which means that when you create a tag that stores less than 4 bytes or 32 bits, it's going to consume 32 bits anyway. Okay, that's the minimum.
What does it put in the blank spaces?
It is unavailable. They'll all be zeros.
Okay.
But you can't access it anyways. Doesn't matter what's in there. So you have a minimum of 32 bits. Now, if it says that it's minimum 32 bits, does that not suggest that you can allocate more than 32 bits for a tag? I mean, does that track?
Depends on what you're using.
Depends on what you're using, but based on I've been really surprised that you did. Based on the data type. The minimum is 32, but you can go up to 64 in a single data type, which would be a real, or for the rest of the world, a floating point value, decimal number. Okay. And then you have structures, which are timers, counters, and that sort of thing, where you have, if you remember from PLC1, and I know it's a stretch for you, but from PLC1, the timer and the counter, you had the preset and accumulated values, which were dense, and then the enable, timer timing, timer done, count up, count down, overflow, underflow, all the control bits were bits, single bits. Okay. So in 32-bit controllers, you have 32 bits allocated for preset, 32 bits allocated for accumulated value, and then you have a single 32-bit word for enable, timing, done, so on and so forth. Okay. So timers and counters actually use 3 4-byte words. Okay. And then you get into string, and it's 32 bits per character. depends on how many characters long your string is, will determine how many 32-bit values you chew up out of your memory. Okay? But point being, 32 bits is minimum. So if I have a double integer, how many bits is it going to allocate for it?
60.
No. $32. Okay. What about a regular integer, which is actually a 16-bit value? How many is it going to allocate? 32. Okay. About a short integer, which is an 8-bit value, is going to allocate 32. Okay? What if it is a bool, which is a single bit? How many is it going to allocate? 32. Okay? There are some instances where if you're allocating bools for discrete objects in your program, it's okay because you got a whole bunch of memory. You're not too worried about running out. So you can allocate 32 bits for every bool, and you use up a lot of memory, but you're not concerned about running out. Okay. But if you have a really big program, lots of tags, that might start becoming an issue. So there are ways to allocate memory in more efficient ways. Okay. Remember what I said about the timers and counters and whatnot? Just use timer for instance. Timer, you have preset, accumulated, enable, timer timing, timer done. Okay. That's a double integer or dent, which is 32 bits. That's a double integer, 32 bits. That's a bool, so 1 bit. That's a bool, and that's 1 bit. Okay. The way the controller will allocate that, I said earlier, these three here are all in the same 32-bit address space in the controller's memory. It only uses 3 of the 32 bits, but that's better than chewing up, 96 for 3? Okay. And then same thing with counter, if you have count up, count down, overflow, underflow, all that kind of stuff. So that's the whole point of that. Minimum is 32 bits. Okay. Conventional PLC, physical address identifies each item of data. If you remember from PLC 1, 500, we had data files, and each data file was specific to a data type. O0 for output data, I1 for input data, S2 for system data, B3 for individual bits or booleans, T4 for timers, C5 for counter, R6 for control register, and N7 for integers, F8 for floating point values or decimal numbers. Okay. In a Logix 5000 controller, you don't have any fixed files like that. We're no longer dealing with data files, we're now dealing with a data base. Okay, so one of the things that you have to tell it whenever you're creating a tag is what data type that tag represents. Okay. Tag types, you have the base tag, which stores a value or values, an alias tag, which represents another tag. So instead of trying to remember local colon 1 colon I colon 0 period data 0, we're going to call it start push button or stop push button, green light, whatever it is. Okay. That's the beauty of tag-based programming, is you get to call it stuff that makes sense to people. Okay. Well, whenever you do an alias, like start push button, stop push button, whatever, you have to tell it what physical I/O point it represents. Okay. Anybody in here have a nickname that they're willing to share? Thank you.
So, my entire family, including my own mother, no one calls me Michael. Everyone calls me Cubby.
Okay.
Straight up.
Anybody else? Audrey?
My dad always called me Skittles.
Okay, I don't want to know the answer. Why on that?
I like Skittles, that's why.
I said I didn't want to know. So anyway, an alias is just otherwise, also known as AKA. If I say William H. Bonney, anybody know who that was? What if I said Billy the Kid? Pretty much everybody knows who that was. Okay. So, the vast majority of the time we use the alias for physical I/O, because we would much rather worry about start push button, stop push button, and so on, rather than local colon blah 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 blah. Okay. So if you think about the descriptors that we put on the data points in 500, instead of using a descriptor, we're using a tag name to make that same connection in our human brains, right? It's known as human readable. Then you have produced, which sends data to a different controller over the network, and consumed, which receives the produced data from a different controller on the network. So that is the tag type: base, alias, produced, consumed. Okay. The data type, as opposed to the tag type. Data type is what type of data is stored in that tag. Okay. Bool, single bit, integers, which includes short integer, integer, double integer, floating point or real, decimal numbers, and then string. Okay. The structures are a combination of other data types. Okay. So, like I said earlier, timer is an example of a structure. Each individual data type in it is called a member, as a member of the structure. And preset accumulator are dense, and then the done, enable, and timing are bools. Okay. So that is a breakdown of what that looks like in your controller. Scope. Anybody remember from last week what I said we were going to do as far as scope?
Every time.
Global. Every time, unless specifically instructed otherwise. Okay. Those are the two types. You have global and you have, which is controller scope. And then you have local tags, which are local to the program that they are created in. Okay. Can't tell you how many times I've seen people create a bunch of program tags and they couldn't figure out why they couldn't see the data on their OIT application. That is because global or controller tags are the only ones that you can transmit over the network. If you have a controller tag and a program tag with the exact same name, it will always use the program tag. Okay. You cannot just, oh darn it, I created program tags instead of controller tags, and then just go and create the controller tags, but it still won't use them. You have to actually delete the program tags and then create them as controller tags. Okay? Controller tag, use any program throughout the entire controller. Must be used in certain circumstances, such as message instructions, produce, consume, and there are a few others that we won't get into in this class. We will if you take PLC3. User-defined tags, or UDTs. This really trips up a lot of people, and I can see why, but at the same time, I can't see why. You know, if you create a timer, you know you have a preset value, an accumulated value, enable, timing, and done, right? Those are all the elements or members in your structure. That's all you're doing with UDTs. Okay, so if I create, motor, and my motor is going to be controlling my conveyor, I create my UDT, which we're going to learn how to do next lab. We're going to do our UDTs, define everything you need to know about motors. You're going to have a start, a stop, commanded speed, actual speed, overload, anything that has to do with a motor. You don't necessarily have to use all of the elements or members of a structure. Like whenever you're doing a timer, you don't always use enable, timing, and done. Frequently, you just use done. Occasionally, you use timer, timing, and extremely rare circumstances, use enable. So, just because it is part of the definition doesn't mean it has to be used. Okay, everybody get that? That's motor data for conveyor number 2. So you notice there, we created a tag just called conveyor 1, gave it a data type of motor, and it created everything below that for start, stop, so on. The period there is the delimiter. In 500, the bit level delimiter was slash. Okay. But you'll also notice that speed command and speed actual, the delimiter is still period. So that's something we have to get used to. Okay. Any sub-element of the main tag is going to be delimited by a period. Okay. But we had conveyor 1 called a motor type that created the other tags below it for us. We have another conveyor, conveyor 2, so we created a conveyor 2 tag, gave it a motor data type, and it created the other tags for us. Okay. When we get to that, you'll see how that operates. So another method to organize your data is to use arrays. Arrays are used in specific circumstances. The most common one that you will see out in the wild, in the real world, is if you need to control very specific set points for speed on a VFD. They come in very handy for ingredients in a recipe. So, you know, how many chocolate chips and how many pounds of flour, and, you know, how many cups of sugar, whatever. Okay. You have all the same data for multiple doodads, then you just adjust the values in an array. You know, if you're making snickerdoodle, you probably put chips in there, so the value of that tag would be 0, hopefully. Okay. Okay. You do have the opportunity to do 1, 2, and 3-dimensional arrays. If you are creating a multi-dimensional array, you want to be extremely careful in doing so because they get very cryptic, very fast, and you will confuse yourself in a heartbeat, if not faster. Okay. For the purposes of this class, when we do get to arrays, we're only going to only going to define single-dimensional arrays. Okay. But, I mean, the melt your brain is not completely fried. So that is an example of a 10-element array. Each one of those is a preset value for motor speed, which you would send to your VFD. Although in that case, there's no data entered in there yet, so all the speeds are 0. We're not going to do anything. Each multi-bit element can be expanded to see the internal components of it. So if you have a short integer cent, you'll have bits 0 through 7. If you have a regular integer, you'll have bits 0 through 15, and double integer will be all 32 bits, 0 through 31. Okay. But notice, pardon me, all of the top data type for motor speed preset. 0 is dent, double integer. And then the sub-elements, period 0, period 1, period 2. Data type on those are all bool, which is the individual bits that make up that 32-bit word. Okay. You guys remember your numbering systems from PLC1, chapter 3?
Yeah. Sort of.
It's a mastery, you should know it like the back of your hand. downhill, I don't know why. Okay, so these are representative of our binary bits. So how many available digits do we have in binary?
16.
In binary?
2.
Can either be on or off, 1 or 0, true or false. Okay. So since we're dealing with powers of 2, 2 to the power of 0, 2 to the power of 1, 2 to the second, 2 to the third. And so, okay, so we think of this as period 0, period 1, period 2, for those of you individual bits making up that integer value. Okay. What's any number raised to the power of 0? Incorrect. 1. There you go. What's any number raised to the power of 1? Itself. Okay. 2 squared, 2 cubed, so on and so forth. Okay. So, motor speed preset 0, say it is set to a value of 10 hertz. What's the binary value going to be? Eight plus 2 is 10. Right? Everything else will be 0. Starting to ring bell now?
Yeah.
So, about a value of 20. 16, 4, 20. Okay. That would be the value it shows up. Here, the ones and zeros, that would say 20. And then next one would be 25 hertz or 30, whatever it is.